We're going to be starting special products to multiply polynomials because sometimes there's going to be patterns that we can see. So let's start with example 1. When we see that square, we want to make sure that we're actually separating that and then taking that chance to FOIL, distribute, multiply it outright, or use area model, whatever method that you're using. So 3x times 3x is going to give me a 9x squared. And then 3x times 4 is going to give me a positive 12x. And then I have another 4 times 3x, which is 12x. And 4 times 4, which is 16. I can go ahead and simplify this, and I'm going to get 9x squared plus 24x, right? These are like terms, plus 16. So this is the final answer. Let's do that again. Right, we have x plus 5, x plus 5. We're going to multiply it out. Except I'm starting to notice a pattern. I notice that if I have a 3x here, the first term is going to be a 3x squared. So take this and this, I'm going to get an x squared, which means I just took this and squared it. So I get x squared. I also notice at the end, right, when I look at this 4, I squared it and got a 16. Okay. So over here, I'm going to get a 25 by squaring this, or just simply multiplying it, right? Or squaring it. In the middle is the tricky part. So now here's the clue. You're actually going to take the first term in the parentheses, which is, in this case, x, the second term in the parentheses, multiply them, and then double it. So in that case, I'm doing 5 times x times 2, which gives me a 10x. And this is my final answer. So this is actually called a square of a sum. There is a pattern to it, so you're going to go ahead, pause the video to take these notes. And you can follow these rules. Whenever you see something plus something, the entire quantity squared, you can just say, okay, a squared plus 2ab plus b squared. Go ahead and pause the video so you can take these notes. Once you've taken the notes, we're going to try example number 3. This is different because we're taking 3x minus 4 and we're multiplying it to 3x minus 4. So once we multiply it out, you get 9x squared minus 12x plus 16. So you get 9x squared minus 24x plus 16. Okay, so if that's my final answer, I'm noticing another pattern. Except we're going to have a subtraction sign. This is called a square of a difference. Go ahead and take these notes and see if you could apply it to example number 4. I have example number 4's answers displayed here, but see if you can actually apply the rule rather than foiling it all out. You can go ahead and pause the video. Let's go ahead to the last one. Now this one, what do we notice about examples 4 and 5? You might notice that they're the same exact terms, but the signs are different. Same exact terms, but signs are different. This is called difference of squares. And there is a pattern to this. But let's multiply it out just to see if we can play with it. So we get 9x squared. We get negative 12x, positive 12x, and a negative 16. When I go and simplify this, I'm just left with this because these cancel out. Okay, this is a rule that you can follow, and this is difference of squares. I'm going to show you the notes for this, and then I want you to apply it to example number 5. Go ahead and pause the video. Once you've taken the notes, take a look if your answer is correct for example number 5 and 6. Sorry, you're going to try number 6, so right, we got x squared minus 25. So we're not just going to sit here and try to see the different ways of recognizing special cases to multiply them out. What we want to do is kind of go backwards. So on the next page, using difference of squares only, this is what you're going to practice. You're going to see, like, if I get an a squared minus a b squared, I can actually undo the distribution and factor it out. So we look to see if there's two expressions. if there's a subtraction sign, if the numbers are perfect squares. You also, let's add another note in here. If the exponents are even, because that's the only way that they can actually be split up, right, evenly, if the exponents are even. Let's go ahead and pause this before we start our examples. And when we look at example number 1, okay, we're looking to see, are there two terms? In this case, yes. Is there a subtraction sign? There is. Are they perfect squares? So now I'm looking at the numbers, right? I have a 1 here and a 4. 1 is a perfect square, 4 is a perfect square. So yes, they are perfect squares. Do not forget that 1's a perfect square, right? 1 times 1. That always tricks people up. And then are the exponents even? Well, this is the only exponent, and yeah, that's an even number. So yes, we can immediately say, well, set it up. We know it's going to be a plus and minus because it fit all the rules to check for a difference of squares. This, a squared, well, what times what gives me a squared? A times a. And then we want to say for the, not even the negative 4, just the 4. What times what equals 4, right? What times itself equals 4? In this case, it's 2. Here's our final answer. And all we did was check each time if these applied. So let's go ahead and try that again. Now I'm going to copy and paste this. You might have to rewrite it or just refer to it. So let's look at example number 2. Are there two terms? Yes, there are. Is there a subtraction sign? No, we stop right there. The minute one of these is not fulfilled, we stop. This one cannot be factored. This one is. So we write prime because it cannot be factored. There's nothing that we can multiply out and get k squared plus 25. Try that again for example number 3. So I'm going to copy and paste my list, right? So we're going to check to see, are there two terms? Yes. Is there a subtraction sign? Yes. Perfect squares is 1 and a 1. Yeah, those are perfect squares. 1 is a perfect square. And are the exponents even? Yes. Let's go ahead and set it up. Do the plus and minus. It does not matter where this plus and minus go. This gets split into xy. And this one gets split into 1 and 1. Here's our final answer. Go ahead and try numbers 4 and 5, since we've tried numbers 1, 2, and 3, and see what you get. I'm going to show the answers, so if you're not ready for the answers, pause the video here. And here are the answers. Check to see if you got them right. Now, there's one other part that we have to keep in mind. In the previous lessons, we learned about a GCF. In these directions, I've noted just to simply factor each difference of squares. I don't say check for a GCF, but we should always be checking for a GCF to see if anything can be taken out before we recognize if it is a difference of squares or a special case. Let's look at number 2. Well, I can rearrange this so I put it in standard form. So let's do that. So I get a negative x squared plus 81. I put it into standard form. Well, standard form, I needed no negatives in the leading coefficient. So let's factor out a GCF. So we have a negative, and we're left with x squared minus 81. Oh, hey, look, this is a difference of squares because of the subtraction sign, because of the two terms. Before, it wasn't set up that way over here. We saw the addition sign in between. But this one is a difference of squares. So sometimes it helps to take out that GCF to make the leading coefficient positive. So between our difference of squares, I get an x minus 9 and an x plus 9. And I need to bring my GCF down. It doesn't just go away. You have to bring it down in your final answer. So you need to be careful with that. Go ahead and practice the next page. And if you practice this page, I'm going to show the answers. So pause it if you're not ready for the answers. But once you're done checking your answers here, try the next page and I'm going to display those answers as well. So if you're not ready, go ahead and pause the video, and when you're ready, unpause it to check your answers. If you need to pause the video so you can check your answers, go ahead. I'm going to scroll down to the second half of the page. So again, this will take time to practice, and you will need to consistently practice this.